Hello dear students, welcome to the class. So we were discussing about the topic semiconductors in which we were dealing with the diodes. Where in the diodes till now we have studied forward and reverse characteristics. In today's topic we are going to study a very important topic called as diode approximation. Okay, so the topic is diode approximation. In the previous classes we have studied about the diodes, its symbol, formation of the depletion region, barrier potential, that is also called as the mean voltage, otherwise cutting voltage. Okay, so the other name is for barrier potential, barrier voltage or barrier potential. Okay. So what is this barrier potential or barrier voltage? It is also called as what? Cutting voltage or mean voltage. 0.3 for germanium, 0.7 for silicon. Okay. We have seen also in the power characteristics that until it crosses that 0.7 and 0.3, approximately I'm writing. Whereas practically the value will be somewhat near 0.3 for germanium and 0.7 for silicon. Okay. A nearer value will be there. We are writing an approximate value. Here, and this is for germanium. This is for silicon. This is what we have studied in the forward characteristics. And also in the reverse characteristics, we have also seen another important voltage that is called as VBR, reverse breakdown voltage. This is also very important. It is the voltage beyond which the junction will be damaged, the junction is going to break out, and a very high current flows, abrupt current flows. Okay, that condition happens in the reverse pass. These points are very important. Right? These points are very important. The characteristics is very important. Right? For the characteristics, how the diode will be biased is also very important. It needs a limiting resistor as well. Okay, this is the circuit. Time resistance. Otherwise, forward resistance also you can say. And this is that. Yeah. For the reverse bias, the circuit is going to be X. You can connect the resistor anywhere in the path. This is called as the limiting resistor. Why this limiting resistor is required? Because as diode is a very sensitive semiconductor component, a large current can damage it. That's why we require a limiting resistor. See, either you can reverse the battery, that means negative this side and positive this side. Otherwise, you can just reverse the diode, that means cathode this side and anode this side. Here, anode this side and cathode this side. Flip the diode, otherwise flip the battery. Anyone needs to be flipped. Okay. Here, this is diode, this is voltage, and this is resistor. We can say it as RV, biasing resistor, or we can say forward resistor. Okay. We normally call it as R. Otherwise, simply you can take it as R1 resistor. Is written. That's okay. And we have also studied about the transition capacitance, where the transition capacitance is going to depend on the area of the depletion region. Here, the depletion region itself is acting as the dielectric medium, and the width of the depletion region, that means how large the depletion region is going to spread, that is going to be resulting into less charges because they are inversely proportional. So basically, the capacitance of the diode, the capacitance amount of charges stored in the diode, and this is under reverse pass condition. Okay? This transition capacitance is observed basically in the reverse pass condition, as the reverse pass is going to result into a wider back depletion ratio. Yeah. So as the width is going to be increasing, it totally going to depend on the width. Yeah. So we have seen transition capacitance from CT here, area by width. Here width is placed in the denominator where distance was placed in the capacitor expression. Okay. How this expression is basically C is equal to epsilon E by E. Okay. The distance between the two parallel plates. Right? This is all the required things I was supposed to revise. Now we proceed with the further topics. We have studied forward bias, we have studied reverse bias. What we are left with is the diode approximation, which is very important, and we will see the specifications. Now the topic diode approximation. So in this topic, that is the diode approximation, basically we will be studying three approximations. First, approximation. The second approximation. And the third approximation. So what are these approximations basically? In the diode approximation, what we are studying here is, we are considering the different cases of the diode. As we have seen, the diode is considered to be ideal. Ideal diode means what? Whenever the diode is considered to be ideal, it simply turns on when the supply is given, and it simply turns off when negative supply is given. That means forward bias and reverse bias. For forward bias, it is going to immediately turn on, and for the forward reverse bias, it is going to be not at all conducting. Here. So basically, these diode approximations are studied for forward bias only. These are basically studied for forward bias only, because reverse bias, all the approximations are similar. It is not like that we are not going to consider the reverse bias condition. But the thing is that the reverse bias condition is the common, otherwise the similar one is the same for all the approximations. Yeah. Reverse bias is same. So basically, we will not consider any reverse bias here. We are going to be considering only the forward biases for each approximation. What are these each approximations in detail we will be studying now. First approximation. First of all, with respect to the VI characteristics. First of all, characteristics and reverse characteristics. In the reverse characteristics, it does not conduct. Okay. Here, so this is reverse voltage, this is forward voltage, this is reverse forward current, this is reverse current. Okay. So we are considering the ideal case. We are considering the ideal case, and in the ideal case, we consider that it does not conduct at all. For whatever voltage applied, how much ever high voltage applied, it will not result in any current. So it is not showing any current. right? And this will remain the same for all the approximations. That's why I have told this one only first. Clear? Okay. So now we will see for the forward bias, but diode approximation, first approximation is for the ideal diode. This is for the ideal diode. It is for the ideal diode. So for the ideal diode, what it says, immediately after the application of the signal, it should start conducting. Ideal case. There should be no delay. Why this delay is appearing? This delay is normally appearing due to the knee voltage. Otherwise, the cutting voltage, otherwise the barrier voltage, VP. Right? So in the ideal case, we consider that there is no barrier voltage. Immediately the voltage is applied. That means even for the 0.1, otherwise even for the least value of the application of the voltage, it should turn on. It should give current flowing. Right? But what is the ideal case? But what is the practical case? That it does not conduct here, it does not conduct even here. It conducts at 0.3 for germanium and even for 0.7 for silicon. But we are not considering that case. We are not considering the practical diode case. What we are considering ideal diode case. And in the ideal diode case, we consider that immediately after the voltage is applied, the current is going to be shoot. Okay. Suddenly the current should increase, right? So like this, maximum current. Maximum current should be resulting in the by immediate application. Okay. So current starts even for least value. Okay. And no VB is affecting it. Effective or effective current starts immediately. Immediately the current starts. Okay. This is for the forward bias. What happens in the forward bias of the ideal diode? First approximation. So when we are considering this first approximation, the diode is connected like this, and this diode is simply replaced by one switch. It is just replaced by one switch. It is replaced by one switch. Just a switch, no other component will be considered. Coming to the circuit as I have told, with the angle bias circuit. This is the circuit. Forward bias. Positive, negative, bias. Okay. And for the first approximation, this circuit will be resulting in a closed switch. This is the bias resistor takes a RB. Okay. This is diode. The current going to this will be I. Okay. So this diode is simply replaced by one switch, and in the forward bias. So in the forward bias, we are showing this. If this is the biasing circuit with the resistor, consider it as RB. Okay, and or simply RA will consider it as diode is simply replaced by a switch. So in the first approximation, diode is replaced only by one switch. Only by one switch. Just a switch. It will be replaced. Yeah. So this is the first approximation. So what the first approximation is basically, ideal diode is considered, and when ideal diode is considered, reverse bias is as usual, it is operating that for the reverse bias there will be no current resulting. Okay. In the forward bias, immediately the voltage is applied, the current shoots. Current starts flowing very high, right? And this is the diode, and a diode is just replaced by one switch. Ideal case, there will be no new voltage affecting, there will be no internal resistance affecting. Okay, so only what is affecting is just the diode operation. That means the diode will turn on for the forward bias and it will be turning on off for the reverse bias. That's it. It is just acting as a switch. So just replaced by a switch. So here in the circuit, it is replaced by just one switch. Yeah. So for this particular circuit, if we are going to, if we consider this as E applied voltage, otherwise just V. So we can write the current equation for this particular circuit. So the current in the first approximation. For first approximation, of diode, IB is given by I is equal to what? What will be the expression? I is equal to V by R. So what is the V here? Only one. And what is the R? The IB. The biasing voltage. So just R you can take it as. Just forward the equation. We have to simply as R. Okay. V by R. Because there is no other component affecting. There is no other factor that has to be considered in the calculation of the current. I is equal to V by R. That's it. This is just acting as a switch, right? So this is the first approximation. So what is the first approximation? First of all, with respect to the graph, immediately the voltage is applied, the current starts flowing. Okay, and in the diode is replaced only by one switch. No other factors. There is no internal resistance. There is no what we can say internal VB, knee voltage. We are not considering anything. We are just considering what? The diode could be just acting as a switch. Immediately the voltage is applied, it turns on. Voltage is not applied, it remains off. Otherwise, reverse voltage is applied under reverse bias condition, it do not cut off. That's it. So ideal case, the diode is shown like this and just replaced by a switch. So in the circuit also it will be replaced by one switch. Okay, diode is acting as a switch. So for this particular circuit, current can be written as V by R. Right? So this is the first approximation of diode. Now we will move to the second diode approximation. Second approximation of diode. We are going to see the second approximation of diode. So for the second approximation, we consider that the diode, not just a switch, but also it is having some barrier potential. So now we are considering the barrier potential. So with respect to the graph, how it can be drawn? The characteristics, with respect to the characteristics. Forward voltage, forward current, reverse voltage, reverse current. Up to the knee voltage, it does not conduct. It do not conduct up to the knee voltage. Okay, and this is the VB. For the VB, starts like this. A straight response. Once it reaches the VB, suddenly the current starts. Does it happen in the practical case? No. But so now we can consider the diode second approximation to be partially, what we can say, ideal, because we are considering the practical value, the practical consideration of the voltage being here. Voltage is there, but what is happening is it is still giving a straight response. But that is not the case with the actual diode. How the diode starts conducting? The diode gradually starts conducting. Okay, so slowly the value increases. Slowly the value is going to increase. Here. So this is the second approximation. So in the second approximation, what we are considering, there is a barrier potential, and up to the barrier potential, it is not going to be conducting. Okay. Up to the barrier potential, it does not conduct at all. This much portion. Okay. Until the voltage, applied voltage level, reaches VB, it does not conduct. Until it reaches the threshold voltage, otherwise the barrier voltage, it does not conduct at all. So when it reaches VB, it starts conducting. Here, the same case for the reverse bias, it does not conduct in the reverse bias. So we are focusing only on the forward bias. So, so in this case, in the second approximation, the diode will be replaced by one switch plus VP. Switch plus VP. So this diode is now considered to be one voltage supply plus one switch. In the ideal case, diode was only acting as a switch. Now it is acting as a switch, but with the internal battery, the VP here, the barrier potential is acting as a internal battery that will be opposing the applied voltage. Yeah. So now considering the circuit, how the circuit is connected. This is the R. This is the diode. This is the applied voltage. Positive, negative. And this is replaced by equivalent circuit having one R, one switch. We are considering it for the power bias. Okay? So for the power bias, it is switch connected, the battery, VB, applied voltage V, current will. So this is the consideration for the second approximation, whereas for the reverse bias condition, if we are going to show it in circuit itself, then we write it as positive negative. It's just replaced by a open circuit. No current. There will be no current flowing. Open switch. Okay. Here, we are going to show it with respect to the diode. It is for all the cases. All the first, second, and third approximation. It's just replaced by one open switch. Third approximation. This reverse bias condition remains the same for all the approximations, first approximation, second approximation, and the third approximation. But it always varies for the forward bias. What happened in the first approximation. In the first approximation, we considered that immediately the voltage is applied, the current shoots up. Okay, suddenly the current flows. That was the ideal case, and we considered the diode to be just a switch. The diode was acting just as a switch, but in this case, the diode is acting as a switch, whereas the diode is also having one inbuilt, otherwise one internally existing barrier potential. And now that barrier potential is considered, and we are reflecting it even in the graph. Okay, we are reflecting it even in the graph. The graph is also showing that the current is going to be resulting into some gap, after some gap, and that gap is called as what? Barrier potential. Yeah. So now this diode is replaced by one switch and a barrier potential. Yeah. So this is the applied voltage. This is the R, and this is the diode. And in this case, in the second approximation, it will be replaced by one switch plus one barrier. Yeah. So now we can write it as, in second approximation, the diode for forward bias is replaced by one switch and barrier potential VB. Okay, that is a battery symbol. Battery symbol that is invertedly. That is invertedly. So in second approximation, the diode for forward bias is replaced by one switch and barrier potential VB. That is battery symbol. So it is showing one switch here and a battery symbol here, one switch here and battery symbol. Yeah. This is the second approximation. And for the second approximation, the current flowing ID for second approximation is given by IB is equal to, so this is the current, I is equal to the expression, normal Ohm's law says V by R. And what is the voltage? This voltage V. There is one voltage V, and there is also a voltage VB that is opposing, that is opposing the battery V here. Right? So we can write it as V minus VB, V minus VB divided by R. Now we consider this resistor R also. So the expression for IB, and diode current now for the second approximation, changes. Why it is going to change? Because now we consider the diode having two components. The diode is basically having internally one switch and one battery. One switch and one battery. Okay. ID is equal to, because of that, what current is given by ID is equal to V minus VB. The applied voltage minus the barrier potential divided by the resistance R. Okay. Here. So this is going to be the total approximation here. Right. This is for the reverse bias condition. This is replaced by the switch, open switch. For the reverse bias condition, for all the approximations, first, second, third approximation, simply the diode is replaced by a open switch here. Whereas for the forward bias, in the second approximation, B diode is replaced by switch plus barrier potential. First approximation, only switch. Second approximation, switch plus barrier potential. This circuit is represented by this form. And from this form, we can write the expression for ID. Here, where ID is equal to V minus VB by R for second approximation. Got it? Right? So this is all about the second approximation. So what we are basically considering is the diode. Okay? Is considered to be the ideal one, that is only replaced by one switch. Okay? And in this case, we are considering the ideal operation of the diode, that it is just acting as a switch. Whenever applied voltage, it turns on. Under reverse bias condition, it turns on. Forward bias, turn on immediately. Reverse bias, turn off. Do not conduct it. This is the ideal case of diode that is considered for the first approximation. That's why in the first approximation, the diode is simply replaced by what? The diode is simply replaced by one switch. But in the second approximation, what we are doing, we are considering the half ideal case and half practical case. Here we are considering only the barrier potential. Still, there is another factor to be considered, that we are going to consider the third approximation. But in this approximation, we are considering the first factor, that is the barrier potential. We know that the diode does not conduct until it crosses the barrier potential, 0.3 for germanium, 0.7 for silicon. Right? So that we are considering now. We are saying that up to the barrier potential it does not conduct, but after that it immediately shoots. But does not happen even in this in ideal case. Okay? So in this case, we are considering that it is going to happen like this. Second approximation. Right? So in the second approximation, what we have done, we are considering the diode to be a switch plus one barrier potential B. That's why the circuit is written like this. This is the second approximation. Now we are moving to the third approximation. What happens in the third approximation? So now about the third approximation. Third approximation. What happens in the third approximation? Considering the graph, first of all, characteristics of the same class. Forward voltage, forward current, reverse voltage. In the reverse bias, we consider it as not conduct. But in the forward bias, what happens? We have already seen the second approximation where it says it does not conduct up to the barrier potential. It will not conduct up to the barrier potential. Okay. And in the second approximation, we said that it immediately shoots, starts conducting. But here we say the current starts in proportion with the applied voltage. This slope is called linear response. And it happens for what? Linear components. And what is a linear component? Resistance. So here we are going to consider that the diode is not only a switch inside, it is not only a barrier potential, other than a battery inside, it is also a resistor inside. Right? So now that single diode is basically replaced by three factors, otherwise three components we can say. That is the battery, right? Sorry, that is the switch first of all, then a battery, that is the barrier potential, and thirdly, now we consider it as a resistor. Yeah. Okay. For forward bias, diode conducts. I am writing for the third approximation. Conducts after the barrier potential and current increases linearly. Current increases linearly with voltage. This is called as linear response. This is called as a linear response. Okay. So, the diode is replaced by diode is replaced by one switch, one barrier potential, which we can write it as S, otherwise this is shown as the closed switch as C, plus one resistor that is called as the diode resistance. Right? Now, how the diode, a single diode is internally having one switch, barrier potential, one battery, and one resistance, that is RD. So these three are basically representing the features, otherwise the characteristics of a diode. The diode is acting as a switch, the diode is acting as a barrier potential, the diode is acting as a resistor. Physically, these components are not connected inside the diode. The diode itself is acting like a switch, it is acting as a barrier potential, it is acting as a internal resistance. Right? This is called as internal resistance of the diode. It is also called as a diode resistance. Right? So how the circuit can be written for this condition? This is the resistor. This is the diode. So how it can be written for the third approximation? This diode, whatever we are connecting here, has to be written in this circuit. Yeah. So this resistor as it is R, this voltage V, and the diode should be having one switch. We mark it as DS now. A barrier potential VB and one resistor RB, that resistance. Yeah. Yeah. Right. This is all about the third approximation. So what we saw in the first approximation, the diode was having a straight response, almost no voltage current was flowing. Okay, that is the ideal case. In forward bias, whenever it is forward bias, it should start conducting, it means. In the second approximation, we consider the barrier potential. We said after the barrier potential, it does not conduct, but once it reaches the barrier potential, sudden current shoots up. Right? That was for the second approximation. In the first approximation, diode was replaced only by a switch. In second approximation, diode switch plus barrier potential, and now switch plus barrier potential plus resistance, diode resistance RD. Right? So that we can see here, diode is replaced by switch, battery VB, and resistor RD. This is the internal resistance, otherwise the what we can say, the diode resistance. So this circuit that is comprising of one voltage supply, one resistance and one diode is replaced by voltage supply, resistor that is a circuit resistance, and the diode replaced by a switch, a direct potential and a resistance. And current flows ideally. Current ID flows. So now the ID can be written as what? Is equal to V minus VT divided by R plus R. What is the current equation? This is the current equation for the third approximation. So this is the third approximation where we are considering the diode to be conducting after the direct potential. Not only that, the response, the current increase is proportional to the voltage. That is a linear response we are going to get in the, what we can say, forward bias condition for the third approximation. And this is considered to be, this response is considered to be for a resistor voltage. Okay. Even for the Ohm's law, we have linear response, voltage versus current. For every step of increase in the voltage, there will be corresponding step increase in the current. That is called as linear. Whenever we are going to observe this linear response, we say that the circuit is observing some resistance. That's why the resistance is replaced by the diode resistance RD here. So the diode is replaced by a switch, direct potential and RD. Okay. So this is the third approximation. The graph is important. This representation of the diode with respect to the third approximation is important. This circuit and with respect to this diode replaced by switch, diode potential and RD has to be written. And this expression for ID is also very important. Okay. In the third approximation of diode, diode is placed by switch, AB and RD, diode resistance. Okay. Yes. So in the third approximation, the diode is considered to be acting as a switch, to be considered to be having one potential, that is direct potential and RD. The diode resistance. So this is about the diode approximation. Very important for finance in the examinations, right? So I'm going to just recall the ID for first approximation, second approximation, and third approximation. The expression for this current ID is very important. That's why ID is given by V by R. Just V by R. Okay. And here, as we consider also the direct potential, V minus VB by R. In the third approximation, ID is equal to V minus VB by R plus R. This is the circuit we considered, and V here, this is the current. This V can be considered as E also, or E. So if we are going to consider it as E, then it is going to be E by R, it is going to be E minus V by R, E minus V by R plus R. Okay. This resistance is R. Okay. So in each cases, of the first approximation, second approximation, and the third approximation, I am just comparing them all together now. So in the first approximation, diode is replaced by just one switch. One closed switch for forward bias and open switch for reverse bias. Clear? Whereas in the second approximation, switch plus direct potential field. Switch direct potential and resistance, diode resistance R. Right? About the graph, we consider a little further. Forward bias. This is the graph. These are the three responses for the first, second, and third approximation. Circuit. That's why V by R, the expression. Second approximation. Switch plus battery. That's why this expression and this expression for second and third approximation. Right? So this shows all the approximations. This particular comparison shows all the approximation. This circuit where diode is just replaced by a switch. That's why ID is equal to V by R. This is the graph with respect to the response for the forward bias. Diode is replaced by a switch plus one barrier potential that can be shown even in the graph that is represented in the circuit. And from the circuit, we can write the expression for ID. Okay. ID. Switch plus barrier potential. That's why the circuit is I is equal to V minus VB by R. Diode is replaced by switch plus direct potential VB and resistance RD. It's a we can say diode resistance, internal resistance. That we can also see observe in the graph. After the VB, current is going to rise linearly, right? That's why the circuit is having one switch, one barrier potential, and one resistance R. Along with the circuit resistance, the limiting current limiting resistance R. That's why the expression ID is equal to V minus V divided by R plus R. This is the summary of all the three approximations. In the first approximation, ideal diode only acting as a switch. Diode acting as a switch plus having one internal barrier potential. Third approximation, switch is having one internal barrier potential plus one internal resistance. Otherwise, it is the diode itself is acting as a switch plus as a barrier potential plus as a resistor. For second approximation, acting as a switch and only barrier potential. Only acting as a switch. Okay. So this is about the third approximation. So totally in today's class we have studied about the approximation. In the further next classes we will be studying the applications of diode. And in the applications of diode we will be studying many applications, out of which in the digital electronics we have already studied. So the diodes are basically used in the digital circuits also. One of the application of the diode used in the digital circuits. Diode is the most famous, otherwise the most important application of the diode is rectifiers. Okay, so in the further topics we will be studying detail about the rectifiers also. Half wave rectifier, full wave rectifier. In full wave rectifier again two types of rectifiers, bridge and center tap. Two types of rectifier we are going to study, right? So apart from that, the diode is having many applications like clipper, clamper. Clipper means some portion of the waveform it is going to delete, otherwise cut. Clamper means it is going to shift the waveform by adding the DC. Here, all these applications will be studying about the diodes in the further next topic, and also the specifications will be studying in the next class, that is forward voltage, forward current, peak inverse voltage. Okay. Specifications of the diode, reverse voltage, reverse current. Right? Peak inverse voltage. What is peak inverse voltage? Means the maximum voltage that can be applied to the diode and the reverse bias. Peak inverse voltage. Beyond that peak inverse voltage, the diode is going to be damaged. Yeah. So all these things we'll be studying about diode in the next class. So what we have studied in today's class is only about the approximation. Apart from this diode, what in the diodes we have studied about the right from the PN junction, formation of the N type and P type semiconductors, the joining, otherwise the half portion of the what we can say substrate, the semiconductor substrate, half portion is going to be the trivalent impurity to form a P type, pentavalent impurity to form a N type, half portion of the substrate is P type, half the portion is the N type, that forms a P-N junction. The separation between the two, P and N, is called as what the junction. Yeah, right. So about the junction, nearby the junction, many concepts we have studied there. That is the formation of the depletion region. The depletion layer is formed. That is going to act as a opposing battery. That is going to act as a barrier potential. Here, that barrier potential opposes the applied voltage, and under forward bias condition, it does not allow the current to flow through the diode unless the barrier potential is crossed. Here. So all these concepts of formation of depletion region, the barrier potential, the height of the barrier potential, the width of the barrier potential, how the depletion region is formed, what happens basically inside that, the diffusion of the electrons and holes that leaves behind the immobile ions that depositate the junction and forms the depletion region. All these concepts we have studied here. So further topics about the diode applications, in which we will be studying about the rectifiers, and rectifiers will be the last topic for this chapter, as the syllabus is quite reduced here. So up to the rectifiers we'll be studying in the next class. Immediately next class we'll be studying about the diode specifications. There we are going to study about the forward current, forward voltage, reverse current, reverse voltage, peak inverse voltage. These will be the specifications of the diode we are going to study in the next class. So in today's class, what we have studied the approximation, the diode approximation, basically having three approximations. First approximation where we consider the diode to be ideal, having replaced by only one switch. That means diode is just acting as a switch. Second approximation, we consider that not only as a switch, the diode also acts as a barrier potential because it is inherent in the diode. We know that the diode is having a barrier potential and the diode is having linear response, but we are studying each parameter step by step in the diode approximation. That is the main concept of the diode approximation. So what we have done basically, first we considered that the diode is only acting as a switch. In the forward bias it conducts, in the reverse bias it does not. Okay. That first condition we considered. In the next condition, what we considered not only as a switch, it is also opposing the applied voltage up to some extent, that is 0.3 and 0.7 to 9 respectively. Okay. So that factor was considered in the second approximation. So in the second approximation, diode was not only a switch, it was also a battery inside. Right? That was the barrier potential. Yeah. That was the consideration for the second approximation. Switch plus battery. And in the third approximation, we considered that diode is not only acting as a switch, only on and off a forward and reverse bias respectively, but also it is having a barrier potential, plus it is also having some resistance inside. So in the third approximation, what we considered the switch, the diode as a switch, we considered the diode as a having also internal barrier potential and also resistance. Right? So these are about the three approximations. First approximation only switch, second approximation switch plus barrier potential, third approximation switch plus barrier potential plus resistance. That was also reflected in the current equation, right? So in the comparison, what I have written in the what I was written in the board, I have written in brief about the current, about the switch replacement, and also the graph. All the factors important for the diode approximation I have executed. Yeah. So the next topic will be dealing with the diode specifications and applications of the diode. This is about today's class, students. Thank you.